The third module deals with Coot. Coot is called the Crystallographic Object-Oriented Toolkit, and it's a program that's immensely helpful with dealing with protein structures and electron density mass and building models. It's a big improvement over former programs. One that I started off using a year ago was called O, and it did work, but it wasn't very user-friendly, and it would crash a lot. It can be very frustrating if you've been spending hours working on a structure and you forget to write out the coordinates. You'd have to start over from scratch. Coot is much more stable. If it does crash, it saves every change that you make, so when you restart it, you can start where you left off. And it's also, in a way, kind of like a video game. It's pretty straightforward on how to use it. So much so that I teach it to my undergraduates, graduate biochemistry students, because it is simple enough to where they can learn how to use it without having to be experts in crystallography. It's very straightforward. So basically, what this is an example of a protein that's in this module that is missing some amino acid residues. So I've gone through, it's a known structure, deleted some of them, just to give you practice in putting them back on. And this is, for example, the N-terminal region of this protein. And you can tell based on the electron density where the residues are supposed to go. One of the things that Coot does is you can add a terminal residue, and it'll put in a dummy residue, not really it's alanine, but that alanine residue will be put into place. And then you look at your protein sequence and say, okay, what is the amino acid residue that has to go here? If it's alanine, fine. If it's one of the others, then you just mutate it to that. But it uses alanine because every amino acid except lysine has a beta carbon on it. And so it more or less should fit. And then once you've positioned it correctly, especially with the peptide bond with the oxygen atom and nitrogen positioned correctly in the density, you can add the side chain and then make adjustments as needed so the side chain is pointing in the proper direction. Sometimes it's hydrogen bonding to something else. And so you have to fit the density and have the proper hydrogen bonding donors and acceptors. So filling this in is relatively straightforward. This is really high resolution data, so that's kind of easy. But if you're dealing with a data set that's 3, 4, or 5 angstroms, not so much. Coot will do a really good job filling in the location of the amino acid residues as you build into this density, but it does still make mistakes even if the resolution is high. So as a protein scientist, you have to understand what the structure should look like and where those atoms are supposed to be oriented, so that you don't build into the wrong density and wind up making some structural mistakes. If you're dealing with low resolution, it'll probably happen a lot because Coot doesn't have that much to go by. So you have to look at the structure and determine where the correct orientation of these different atoms are. Now, in the event that you do have some bonds and angles that are off through the model that you built, Coot has the ability to regularize and do some structure-based refinement so that it will make some corrections based on how it knows what the bonds and angles are supposed to be for these amino acid residues. So you can fix it, even if you put in something and it doesn't look quite right, you basically can do a very simple refinement, sort of real space refinement is the function that it's called, and regularize the bonds and atom lengths so that the distances and angles are correct. So there are ways of dealing with that. And even, of course, if you go to deposit your protein ultimately in the protein data bank, there will be a check there, part of the validation process of running Ramashandran plot, which you probably should be doing anyway. And we'll let you know if some of the phi and psi angles are off so you can correct them. Sometimes they will be, sometimes they're in the forbidden zone or the generously allowed region, what they generally call it. And that could be okay if there aren't that many, or if it's in a region of poor density, or that particular residue is involved in part of the enzyme mechanism that's under strain. But if half of your residues look that way, then something's wrong. We better go back and fix them. And it's always worth checking to make sure that those numbers do correspond with something that is correct in your structure. If you need to fix it, then go back and double check that. So there's different ways of looking at how to build in the density. Again, with a high resolution structure, you can tell where the residues are supposed to go, but the skeletonization will show you kind of like a path of where the atoms could potentially go. And this is very helpful when dealing with lower resolution data sets. It's possible to go straight to an amino acid residue if you want to. That's really helpful if you know, for example, an amino acid residue that's involved in catalysis or binds a particular ligand, whatever. You can easily navigate to that by typing in the number here instead of trying to find it with protein. And also the go to next ligand function is very helpful if you're trying to find where the ligand binding sites are, which is usually one of the most interesting things in a protein. Go straight there and see how the active site or the ligand binding site is organized. So while we're doing this, we're building into electron density. What Coot will do, it will add an alanine residue generically because it has some beta carbon. And then you go through your actual sequence and see what it's supposed to be, and you can mutate it to the correct residue from there. So this is an example of that. I have an example of the protein we're looking at here is lysozyme, very famous protein that's very easy to crystallize. And there's over 1,000 data sets in the protein data bank on. This one just happens to be really high resolution. There's a little cysteine cross-link that's here, so you can see what that looks like while building. And this is an example of sometimes where the amino acid residue is positioned. Clearly, it's not, the side chain is not correct, but it is in a position where you can tell where it's supposed to be. This phenyl ring here, phenylalanine, just needs to be rotated into this until that shade density here, very clear. Or an example of a lysine residue that's sitting here that needs to be pushed in the other direction. The nitrogen atom can be over here instead of where it was oriented. So that's an easy fix as well. And then when it comes to model refinement, after you've done producing your new model, made changes to it, you can go through and do model refinement where the model will be improved upon. You can add water molecules. It'll correct some bond angles and distances, and then ultimately improve the structure in a way that makes for improved electron density maps that you then continue to use. And this process goes over and over again until there's no additional changes to the structure that can be made to make it better. At some point, there's really nothing you can add to it. You've added all the residues, you've added every ligand and water molecule, everything looks really good. Well, at that point, you can't refine it any further improvements, which means the maps aren't going to be any better. And so once you've gotten to that point, you're ready for depositing in the protein data bank. So you've got this, at this point, basically what happens, within Phenix, Coot will run, the electron density map will show up, and this will kind of change over time. Ultimately, though, you'll land on a final refined structure that you can visualize in Coot. So that's the end of the 3 modules that deal with protein crystallography, and it deals with the major programs, data collection, just a discussion of it. This one thing that we don't talk about in these modules is the data collection process itself and scaling using a program like ScalePack. That's done either at the electron source, whether it be a synchrotron or a home source. Once you have scaled data, then the scaled data are used as the initial reflection used to solve the structure. And so we kind of take it from there. But dealing with solving structures with anomalous methods, dealing with molecular replacement, and then model building, refinement, visualization, and Coot is a really good start to begin discussing protein crystallography and learning about how to use it as a practical application in research.